Welcome to a presentation on momentum in two dimensions. What we'd like to start with is just a quick review of a straightforward momentum collision. In this case, we have an example of a pool ball that's going to the right, hits the wall and bounces off and straight out. And so in this case right here, we'll say that the ball goes in with a momentum of 5 units of momentum, hits the wall and rebounds directly back with 5 units of momentum in the opposite direction. And we'd like to know the direction for the change in momentum during the collision and also the numeric value for that change in momentum during the collision. So go ahead and make those computations, draw an arrow representing the change in momentum and find its magnitude, and pause the presentation, and then check back with my solution when you're finished. All right, I'd like to go ahead and use a vector technique for showing the direction for the change in momentum in this case. And the way we'll do that is this. If you draw the initial vector, so in this case we have the initial momentum vector is going in this direction. The final momentum direction is something like this. This is my final momentum. And then we ask ourselves, what do we have to do with the first arrow to make it look like the second arrow? In other words, if we treat the head of the first arrow as if it's a handle, and we grab it, what do we have to do with our hand to force that vector to make it look like the second vector? Well, it's pretty clear it's going to be something like this. I'm going to grab it, I'm going to jam it basically through itself to get rid of the momentum in the first case, drag it all the way through to the other side, and you get this vector, which represents, in this case, the change in the momentum during the collision. Now, what's nice about using this method here is you might be tempted in this case when you have an example like this where the momentum into the wall is 5 and the momentum out of the wall is 5, you might be tempted to say that the change in momentum is 0. But by using this vector technique, it'll be very clear to you that this is not a collision where the change in momentum is 0. In fact, the change in momentum must be greater than 5. How much greater than 5? Well, now we can just go ahead and apply the math to that. The change in anything, change in momentum in this case, is equal to the momentum final minus the momentum initial. The final momentum in this case is going to the left, so it's going to have a negative sign, minus 5, minus the initial momentum, 5, and we get a total momentum change of minus 10, which brings us back to the longer change in momentum vector. All of those things coordinate. That's a little review of momentum change and collisions. Now, one thing I wanted to point out here before we move on is the importance of this vector that we've designated here as the change in the momentum vector. It turns out to be a very interesting and important vector in this sense because it points in the direction of a whole bunch of other things that we're interested in. We know that momentum is equal to mv, so change in momentum is equal to the change in the mv, and if your mass isn't changing, then it's also the same direction as the change in the velocity. So we could write here, for one example, this direction of my change vector is also the direction of my delta v. Well, acceleration is equal to change in velocity with respect to some time, something like this. So what that means, of course, is this is also the direction of the acceleration of the object at the moment of the collision. And we know that the net force is equal to the mass times the acceleration, and that's going to help us understand that this is also going to be the direction of the net force on the object during the collision. And you can kind of see the fact that this, the importance of this change in momentum vector here, because it points in the direction of all of these things that we also might be interested in. Okay, so that's just a quick review of a one-dimensional collision problem. Now we'll try a collision involving two different dimensions. So in this case, the ball comes into the wall at an angle of 45, and we'll say it bounces at an angle of 45 degrees as well. Let's see, for simplicity's sake, let's just go ahead and say that the momentum into the wall for this collision is equal to 5 units, and it also has 5 units of momentum when it comes off the wall on the other side. Similar in the other case, what I'd like you to do is go ahead and solve for the direction for the change in the momentum during this collision, and also the magnitude of the change in momentum for this case. Go ahead and pause the presentation, do your own solution, and then check back with mine. All right, let's start with the vector addition. In this case right here, we'll use the same procedure that we used before. We have the initial momentum, P0, pointing in this direction. The final momentum looks something like this, P1. We ask ourselves, what do we have to do with the first arrow to make it look like the second arrow? Well, if we grab this head and we pull it in this direction straight up, something like that, we get our delta P, in other words, our change in momentum during the collision. Now, how can we turn this into a numeric answer? Well, in this case now, you can see we're dealing with angles, but there are a couple things that are going to help us simplify this problem. One is the thing that we noticed before about the direction of our change in momentum vector right here. So in this case right here, remember that that change in momentum vector also points in the direction of our, we said our delta V. So delta V points in this direction. Our acceleration must be pointing in this direction, and our net force must be pointing in this direction. Now that should make sense if you think about this. When this ball comes into the wall, it contacts the wall for just an instant. But at that instant, if we were to let's say we were to blow up the diagram a little bit, you would see something like this. You would see the ball coming in, and then for just an instant, you would see it contacting with the bumper right here. But at that moment of contact, notice there's only one point of contact, and the net force acts directly away from that contact position, something like this. So that, anyway, that all corresponds with what we talked about before with these other vectors. Well, why is that important in this case? Well, if you take a look at it, if my net force is directly away from the wall, the acceleration is totally away from the wall. That means there's no change in these quantities, no change in the motion of the object from right to left. What it means is this. This ball we can consider as coming into the wall with a certain momentum in this direction, but it also has a momentum in this direction, two components of its momentum. We might say an initial momentum, let's call it the y direction. In other words, we'll set up a direction, something like this. We'll have the y-axis going in this direction and the x-axis going in this direction. And then we have a component of the momentum, initial, in the x direction going this way. Similar, when it comes off of the wall, it's continuing forward, so it has a momentum after the collision in the x direction, but it's moving away from the wall, something like this, so we have a momentum after the collision in the y direction. And what our analysis shows with this collision with the wall is that the momentum before the collision in the x direction equals the momentum after the collision in the x direction, so we don't care about that direction. So in other words, all of the change happens in the y direction. How can I calculate the numeric value for that now? Well, you can see here that we can just use a little bit of trig. And in this case right here, if we were to take a look at these, this angle here, we would notice that we've got this angle right here is equal to our 45. The momentum change in the y direction is touching that angle. So we can say now, instead of working with the x direction, if we go and work with the y direction, we would say that the momentum initial in the y direction is equal to our initial momentum times the cosine of 45. Similarly, we can solve for the momentum after the collision in the y direction, and you'll see that's going to be the final momentum times cosine of 45. And we were able to basically use trig to solve for these two components here. And now to just complete this thing is going to be 5 cosine 45. This is 5 cosine 45. You can see based on this direction here that the total change is going to be twice this value, 10 cosine 45. in the positive y direction. And you can see here that now what we've done is we've used momentum in two different dimensions and a little bit of trig to solve for our final value for the change in momentum during the collision. That's the technique that we'll use to solve now for more complicated problems when we have more than one object. So here we go. In this situation, we've got two objects, object A and B. The momentum of object A, well, we'll keep everything the same as it was before. We'll say object A is rolling to the right with 5 units of momentum, and it strikes object B, which is at rest. After the collision, the two balls go off, and you can kind of see 45 degrees from kind of the center line from before. And what I'd like you to solve for in this case now, we're not going to solve for the change in momentum. What I'd like you to solve for is the final momentum for object A and the final momentum for object B. And you can go ahead and pause the presentation, see if you can solve for those, both the direction, well, we got the directions, the magnitude of those two vectors, and check back with my solution when you're finished. All right, this is an example where a calculation where we would use the conservation of momentum. And the basic idea of the conservation of momentum, of course, is that the momentum, in this case P, for the system, for the entire system before the collision has to equal the momentum of the system after the collision. We might write it something like this. If we were to write it in vector form, we would say the momentum of object A before the collision plus the momentum of object B before the collision has to be equal to the momentum of A after the collision plus the momentum of B after the collision, something like this. We know the momentum of B happens to be 0, so we'd have a statement something like this. We are given in this case that the momentum is equal to 5 for A, so getting rid of kind of cleaning up that side of the equation, we get something like this. 5 is equal to this plus this. But notice that in this case, these are vectors and they are not pointing just to the left and the right. So we cannot say that the momentum of A after and the momentum of B after is numerically add up to 5. It's not 2.5 and 2.5 for these two vectors. That's not our solution. But based on what we did in the previous problem, we noticed that we can use a little bit of trig, and using the idea of the momentum in two different directions, we can go ahead and figure out what our total momentum for A and B is after the collision. And this is how it works. Notice that we can break up the momentum of each of the objects in both our x and our y direction. So we can say that after the collision, A has a certain momentum that's going in the x direction, and it's a certain component of the momentum that's going in the y direction. Similarly, B has a portion of its momentum vector pointing in the x direction and a portion of the momentum vector going in this direction. We can use trig to actually assign values for this. I'm going to do this over to the side so that we have a little bit more room here. But with our 45 degree angle, we know that this is going to be this momentum of A after the collision, which is our hypotenuse, times the cosine, because it's touching this angle right here, of 45. This component right here is going to be our momentum A after the collision sine 45, something like this. And we can do the same thing with the other vector. It would be like this, the momentum of B after the collision times the cosine of 45. And in this case right here, the momentum B after the collision sine of 45. Having to squeak it in here in the corner. There we go. Okay. And so now we have our components. Now, taking a look at this, and again, simplifying, we know that this, when we look down at our basic relationship for the conservation of momentum, we know that the momentum of the whole system before the collision is 5, So the momentum of the system after has to be equal to 5. But notice that the 5 units of momentum are all pointing to the right. And so it turns out in this case right here that after the collision, you have to have 5 units of momentum pointing to the right. And the only components that are pointing to the right are these components right here. This one and this one. So what you can say here in this case right here, therefore, is that coming down to our equation right here, this momentum, the 5, is equal to the momentum of A after the collision in the x direction plus the momentum in the x direction for object B. Now in this case it's symmetrical, they're going to be the same, so each of these will be equal to 2.5 units of momentum. In other words, not the final momentum of this after the collision, not this number, but this number right here is going to be half of the original momentum for your system. How's that going to allow us to solve for the actual momentum of A after the collision? Well, we're just going to set this number now equal to our 2.5, and we can solve for the momentum of A after the collision. And that number ends up, let me go ahead and fill it in up above here. Let's see, that's the answer that we're looking for right there. And that answer is, we'll call it 3.5. So this answer that we're solving for is 3.5 units of momentum in this direction. Again, since I've given you an example that's symmetrical, this answer for B will be the momentum of B after the collision will be 3.5 units of momentum at an angle of 45 degrees off in this direction. And that's how you're able to solve for momentum change and momentum problems that are done at angles. Now, what I want to do real quickly here before I sign off is to go back to this idea of momentum change. In this case, what we did was we used the general idea for the conservation of momentum. But we could also think of this in terms of momentum change, and that would be helpful in this case as well. Let's take the momentum change for object A first. You can kind of see that object A starts with some kind of a momentum in this direction. We said that that's equal to 5 units. It ends with some kind of momentum, 3.5 units, kind of in this direction. So this is our initial momentum, this is our final momentum for object A, and see now you can kind of see that the change in momentum vector for object A is going to look a little something like this. If we did something similar for object B, it would be like this. Object B has no momentum beforehand. It has a momentum that's in this direction, final, which means all of its change is in the direction of its final momentum. In other words, that's what I have to do to it. That's my change in momentum for object B. Now, the interesting conclusion here, you'll notice, is that these two vectors are pointing in opposite directions, which should make sense now in the sense that at the moment of contact, they have a single point touching each other. Each of their change in momentum vectors is in the direction of the acceleration and the direction of the net force, which acts perpendicular to that contact point at the moment of the collision. It also means this. It means that the total change of the momentum for the system, in other words, if we take the momentum change for A and add it to the momentum change for B, you should see that the total change in momentum for the system in that collision is equal to 0, which we'd expect if momentum is conserved. There's no overall change in momentum for the system totally. So this is the general procedure that you'll use for dealing with momentum problems in 2 dimensions. I'll suggest some textbook reading for you and give you some example problems to help you through the finer details of these types of problems. Thanks for joining me.